Alright, welcome back everybody. We are moving into Chapter 2, talking about descriptive statistics. So, in Chapter 2, we're going to be looking primarily at two main things. We're going to be looking at visual representations, graphical representations of a lot of the tests that we run, the data that we use, different ways that we can display it to make it easier to understand and to read. And we're also going to be looking at some measurements of data, so looking at some of the things you commonly associate with statistics like mean, median, mode, that kind of stuff. So that's all coming up in Chapter 2. So let's go ahead and get started with the graphical representations. So in Section 2.1 we're looking at stem and leaf graphs, line graphs, and bar graphs. So to start off, we're talking about a stem and leaf plot. This is a way to represent data that is similar to a histogram, which we'll talk about a little bit later. To draw a stem and leaf plot, each data value must be broken up into two components, the leaf and the stem. So basically, what we're doing with the stem and leaf plot is we want to be able to write out all the data in a more efficient way, so we don't have to write each data point over and over again, but then in a way that we can still see what the data is. Okay, so for example, here up in the box still, for the number 173, the stem would be 17, the leaf would be 3. Okay, so the stem consists of all digits except for the rightmost digit. So, like if we had, in this example down here, we have the number 33. So when we're drawing the stem and leaf plot, the stem is the 3, the leaf is the last 3. Then we have 42, like that. And then we have 49 and 49. So instead of just rewriting 49 and 49 again, I already have the 40 right here. So I'm just going to add a 9 there on this side. That covers one of them. And then you have to put duplicates as well. So there's another 9 there. So by writing it this way, now we can read this as 42, 49, and 49. Okay, so 3 data points all consolidated into one little section here. Okay, so it's very helpful to write it more concisely this way, but still see what the data is. And it also gives you an idea of where the data is grouped the most. So you can see, right, there's more data here at 4 in the 40s than there is in the 30s. Okay, so that can also be helpful, a helpful way of reading that. So if you look at the next page, they actually did this one for us. So this stem and leaf plot shows that most scores fell in the 60s, 70s, 80s, and 90s. 8 out of the 31 scores, or about 26%, were in the 90s or 100s, so a high number of A's. Okay, so if we look, and you can see, right, there's the 33, the 42, 49, and 49, 53, 55, 55, etc., etc. Okay, and then if you're looking at the shape of it, you can see where the data is spread the most. Right, so kind of like they said, right in here, 60s to 90s is where most of the data is. So that can give us good visual information as well. Okay, so that's a stem and leaf plot. Then we have a frequency polygon. So frequency polygon is a line graph where a point is placed on the midpoint of each interval at height equal to the frequency. Okay, so the frequency is just the number of times it occurs. Typically the points are connected with straight lines to emphasize the distribution of the data. Alright, so let me get a thicker pen here. Alright, so from 140 to 179, okay, so we're drawing a frequency polygon for the cost of textbooks. The midpoint is 160, so that's down here. The frequency is 4, so that means that I'm going to plot a point here at 4. Alright. Then from 180 to 219, the midpoint of that is 200, so they've already labeled all the midpoints here. There was only one textbook that fell into that category, fell into that range of cost. So that one just has a value of 1. Okay, and then we keep going. So the next Next group has a midpoint of 240, and that one occurred 4 times, so that's right there. Next one, 280, occurred 6 times. 320, that group occurred 10 times. And then 360, that group occurred 6 times. The 400 midpoint, that group occurred twice. 440, that group occurred 3 times. Alright, and then we go ahead and connect the dots as best we can. And we always go ahead and just start with zeros on the corners, right, on the edges. That's going to make it connect. Okay, and then this one, I'm not sure what happened there. So there's a point right there. So we've got that, that, and finish this off, bring it back down to 0. Alright, and there is our frequency polygon. Okay, so the frequency polygon, it's called a polygon because it is a shape, right? You can look at the connected form of it, right? It's multi-sided. And then it gives us accurate information about what's going on. So you can see where most of the cost of the textbooks is right up here, right? So right in the middle of all of these ranges is where most of the textbooks are. Alright, so that's a frequency polygon. Then we come to bar graphs. So bar graphs, usually pretty common, so everybody usually recognizes a bar graph. This is a graph that displays a rectangular bar for each category where the length of the bar indicates the frequency of that category, right? So however tall the bar is, that's how many data points you have there, right? There's a horizontal and vertical axis. The horizontal axis lists the categories, the vertical lists the frequencies. So for this example, by the end of 2011, Facebook had over 146 million users in the United States. The table shows 3 age groups, the number of users in each age group, and the proportion of users in each age group. Construct a bar graph using this data. Alright, so let me make some axes here. There we go. And then we're going to have 3 groups on the horizontal axis. So we're going to have, if you look in the table, the age groups are going 13 to 25, 26 to 44, and 45 to 64. So those are each going to represent their own bar in the bar graph. And 26 to 44. And 45 to 64. Okay, so down here this is our age group. And then up here we're going to have number of users in millions. Right, so in millions, so I'm going to count up, let's see what we have here. We have a 27 million, a 53 million, and a 65 million. So I'll just go by tens. So 10, 20, 30, 40, 50, 60, 70. $40, $50, $60, $70. Okay. Then our bar graph, we need to draw the rectangle for each category and make sure it has the corresponding height. So for this first one, The age group of 13 to 25 has over 65 million users. So that's going to be somewhere right in the middle there, between 60 and 70. The age group from 26 to 44 has about 53 million. So that's going to be somewhere right around here. Okay, that's a little bit above 50 million. And the age group from 45 to 64 has about 27 million. So it's going to be a little lower than 30. There we go. And then we can fill these in. Alright, and that's our bar graph. So you can see, if you're just visually looking at this, and you notice that age is increasing as we go this way, but notice the number of users is dropping as we go that way. So that can give you some quick information about what is going on in this scenario with this data. So that is a bar graph. And that brings us to the end of 2.1. So now heading into 2.2, we're looking at histograms, frequency polygons, and time series graphs. So a histogram, this is one of the most commonly used diagrams in statistics. So this is similar to a bar graph, but for quantitative data. Histograms have a horizontal and vertical axis, where the horizontal axis lists the values in the frequency table, and the vertical axis lists the frequencies. Okay, so horizontal is the numbers, vertical is how many, right? How many of each do we have? Okay, the rectangular bars in a histogram, unlike a bar graph, these rectangles do touch each other. They do come right up against each other. So for this example, below are data of 16 randomly selected weights in pounds of models from a model agency. Construct a histogram from this data. So what I'm going to do is I'm actually going to use technology, show you how to do this with technology, and we'll be looking in just a little bit at an example we're going to do by hand. But for this one first, we're going to hop onto Desmos for this one. Okay, so Desmos, great tool for especially for these types of graphs. So what we would need to do is we would need to take each of those weights, put them into a table in Desmos, and make sure to put them down the correct number of times. So I'm going to switch over now. Okay, so if you look on my upper left-hand corner here, you can see I have all of the data up here. Notice this is a 16 element list. So it's got all 16 data points in it. And then all we need to do, once we have that data set, is just type histogram of the data set. And when we do that, turn it on, this is what we get. So let me zoom in here. And there you can see it's kind of small because our scale is a little wonky here, but these are rectangles, right? And on the horizontal axis, you see, right, we've got like an 85 down there, 100, and then up on the vertical axis, it's measuring their counts. Okay, so and we talked about, right, the histogram, the rectangles touch each other, and you might be wondering, well, these aren't touching each other. Well, the reason they're not touching each other is because they're too far apart numerically. If you wanted to, we could make these rectangles wider. So I could give them a width of like 10, like this, and it starts grouping the data together a bit more. And you can see now they're coming right up against each other, but just for the sake of maintaining that individual data, I'm just leaving it with a width of 1. But we can make wider histograms as well. Okay, and there we have it. So this is what our data looks like. Okay, and then you can start looking for patterns, looking for trends, things like that. So there are different ways of creating histograms using different software, using calculators, but I'll always pretty much use Desmos for it. So there we go. All right. Oops. So here's the calculator steps if you happen to use the TI-8384. Now let's look at an example where we're actually going to draw one. So the total cost of textbooks for the term was collected from 36 students. Construct a histogram for this data by hand and by using the calculator. So we're going to do it by hand, and then we're going to also use Desmos just to confirm that we get one that looks similar. Okay. So this data we were looking at earlier, right? We drew a graph for it. It was a frequency polygon, but now we're looking to do a histogram. So let's start with labeling our axes. Okay. So we're going to go ahead and label using the midpoints. Okay, so the midpoints, we're starting at 160 and counting up by 40s. So I'm going to start labeling. So that's 160, 200, and I'll make my text smaller in just a second to make it fit better. 240, 280, 320, 360, oops, 400, and 440. Let me shrink that down just a little bit. There we go. That's pretty good. And then shift that over. Well, actually, sorry about that. We're just playing around with this a little bit. There we go. That's pretty good. Okay, so now you can see those midpoint values. On the vertical axis, notice we go as low as 1, as high as 10. I don't have 10 tick marks on here, so I'm just going to count up by 2s. So that's 2, 4, 6, 8, 10. Okay, and now we go ahead and draw rectangles that are centered around these midpoints. Okay, so around the midpoint of 160, I want a rectangle that has a height of 4. Okay, so let me actually make this blue, and let's fill it in blue as well. Okay, so height of 4, centered around 160. There we go. Close enough. And then centered around 200, that one has a height of 1, so we've got to give it a height of 1 down here. So it's pretty small one. And they are going to touch. Next one, we have a height of 4, centered around 240. So another one that's kind of that same height. Okay, and then 280, we have a height of 6. And theoretically, these are all supposed to be the same width, but a little bit wider. Good enough. Okay, and then next one, around 320, we have 10. So this is our tallest one. And then centered at 360, we have another height of 6. Centered at 400, we have a height of 2. And then centered at 440, we have a height of 3. Alright, and there we go. We have our histogram. So this gives us the same data that frequency polygon gave us before, but this is a more common method that we have for drawing this out. So now I'm going to come back to this in a sec, but let's look on Desmos as well. So here you can see I already put in the data, so it's a 36 element list, so I put it all in there, and then I did a histogram of that data, and I set a bin width of 40 because in the problem it broke it down into cost groups of 40. And that is right there. And if you compare that to the one that we drew, you will hopefully notice that you can see it on both there. It's exactly the same. Alright, so our histogram looks good. Okay. So there's a brief note that they want to just mention. For drawing histograms with grouped data, we can use the midpoints of each class or the lower limit of each class. Typically, I personally use the midpoint just because I think it centers it a little bit better, makes it look a little nicer, but it just depends on the situation. You might use the left-hand endpoint, and that's okay too. Okay. Then there is a time series plot. So a time series plot is obtained by plotting the time in which the variable is measured on the horizontal axis and the corresponding value of the variable on the vertical axis. So a time series plot is just plotting kind of like a frequency polygon, but the horizontal axis is time, so as time passes. So here's an example of that. So we have the data showing closing prices of the Dow Jones from 1990 to 2007. And then we have a time series plot for the data on the left. So you can see here, right, as time passes, we're measuring these values. Right, so we've got all these different values being measured as time passes. So that's the only difference between a time series plot and a frequency polygon, is that the horizontal axis is time. All right. And that brings us into section 2.3. So now we're going to talk about measures of the location of the data. So we're going to start off talking about the concept of a percentile. So the kth percentile, denoted P sub k, of a data set is a value such that k% of observations are less than or equal to the value. So let's say that again. K% of the observations are less than or equal to that value, right? So you commonly hear examples revolving around like test scores, right? And there's an example up here. Someone scored in the 90th percentile of the exam. That does not mean that he got a 90% on the test. It means that he got a test score that is higher than 90% of the other scores. Okay, so I'll say that one more time. So if he scored in the 90th percentile, it doesn't mean he got a 90%. It means he scored higher than 90% of everyone else. Okay, so, if everybody else, if 90% of people got an F and he got a D, then he could still be the 90th percentile because he scored higher than 90% of everybody else, regardless of what his actual score is. So for this example, the graduate record examination, so the GRE, is a test required for admission to a lot of U.S. grad schools. University of Pittsburgh Grad School of Public Health requires a GRE score no less than the 70th percentile for admission into their Human Genetics MPH or MS program. So what is this telling us? It doesn't mean you have to get a 70% on the GRE to get into this school. It means that you must have a score higher. You must, let me write that with proper grammar. You must score higher on the GRE, then 70% of all the people that took it. Okay, so it's not about the actual score you got necessarily, it's about how you did comparatively. Okay, so that's what we mean when we say percentile. So now the concept of a percentile brings us into what we call quartiles. So a quartile is actually how we divide up data. When we're looking at large sets of data and we want to look at kind of groupings of it, we group it into quartiles. So there are going to be 3 quartiles. So there's the first quartile, which we call Q1, has 25% of the data below it and 75% above it. The second quartile, or Q2, which is also called the median, is quite literally the middle. It's the middle value, where 50% of the data is below it and 50% is above. And then there's the third quartile, Q3, where 75% of the data is below it and 25% is above it. So these are called quartiles because they split the data into quarters, right, into 4 pieces. So quartiles divide the data into 25% groups. Okay, and the interquartile range, the interquartile range, which we call IQR, is Q3 minus Q1. So what does the IQR tell us? It tells us where the middle 50% of the data is. Okay, if we want to look at the middle, then we look at the interquartile range. Okay. And we will do some work with the quartiles in this section. So note, the quartiles are the 25th, 50th, and 75th percentiles. Okay, right? Because 25% below, 50% below, and 75% below. And Q2 is another way of defining the median. Median meaning the middle value. Okay, and that's exactly what I just said here. So the median is the middle value. Alright, so here's more of a visual representation of what the quartiles look like. So there's Q1, Q2, Q3, and we have 25% of the data blocked into these quartiles. And then of course there's the minimum and the maximum value as well. These values bring us to what we call the 5-number summary. Okay, so the 5-number summary includes the min, the max, and all 3 quartiles. Okay, so this can give us very useful information when finding the quartiles, when finding the data set, because it can tell us how spread the data is. It can tell us, is a lot of the data really low, really high? Is there a lot in the middle? So these are all things that we need to look at when dealing with the 5-number summary. Now, when you're obtaining the 5-number summary, okay, they're giving a step-by-step here, but basically you're just trying to find the middle of everything. So first you find the smallest value, that's the minimum. Okay, of course the largest value is the maximum. Then you want to find the median, or the second quartile. Okay, so what you want to do is you want to just find the middle value. So you go right into the middle of the data set, that's your median. If there is no single number to let you find the median, then you need to take the average of the 2 middle numbers. Okay? And we'll see an example of that in just a second. And then you do that similarly for Q1 and Q3 by splitting those in half. So let's look at an example. So here we have the data of 16 randomly selected weights of models from a model agency. Find the 5-number summary and include the interquartile range. So what we're going to have, we need the min, we need Q1, we need Q2, Q3, and the maximum. Okay, and then let me just put in the Q1, Q2, and Q3. There we go. Okay. So when we're looking at the data set, so we can find the min and the max pretty quickly. So the smallest value is 85, largest value is 138. So the min is 85, the max is 138. Okay, now to find Q2, which is also the median, we need to start working our way towards the middle. So we have 16 data points here. So that means I'm going to cut that in half, so that's 8 on each side. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this right here is where Q2 is. Now, it's not a single value, right? Because there's not one value in the middle. So what we have to do is take the average. Now, lucky for us, these two are the same number, so it's not going to matter, but we would just need to do 110 plus 110 over 2, which of course is just 110. But that's the process that we would use. Okay, so the second quartile is 110, so that means half the data lies below that number. Okay. Then to find the first and third, we need to split these in half. Okay, so now I have up here, I have a set of 8 data points. Half of that is 4. So I'm going to go 1, 2, 3, 4, and 1, 2, 3, 4. So the middle here is between the 85 and the 98. Okay, and so now we do really need to do this calculation. So this is 85 plus 98 over 2, which is 91.5. So that's our first quartile. So that tells us that 25% of the data lies below that number and 75% lies above that number. Okay, and then we do the same thing for the third quartile. So we have 8 data points, so 1, 2, 3, 4, 1, 2, 3, 4. And we're right in the middle again. That's Q3, and it's between 115 and 115, so we know it's going to be 115. Okay, and that is our 5-number summary. And then it also asked us for the IQR, that interquartile range. So remember, that's just Q3 minus Q1, so it's that middle 50%. Which in this case, that's 115 minus 91.5, which is 23.5. So that means the middle 50% of the data falls within a range of 23.5 units. Okay. Now, sometimes when we're dealing with data like this, you can get data points that are what we call outliers. So outliers are data points that are really far out there away from the data set that can start to skew our results. So we always want to check to see if there are any outliers in data sets so that we know, is there a data point that's really pulling my averages? Okay, so first we need to determine Q1 and Q3. Okay, find the IQR, that interquartile range, and then determine what we call the fences. So the lower fence and the upper fence are what we use to identify where the outliers would be. So we take the first quartile and subtract 1.5 times the IQR, and that gives us our lower fence. So that tells me, right, all my data is in here, and my lower fence is right here, right, keeping all the data in from the bottom. The upper fence, you start at Q3 and add 1.5 times the IQR, and that bounds in my data above. Then the question is, were there any data points out here, right, out beyond those fences? Those would be considered outliers. So let's look at the example we just did. Are there any outliers in this data set? Well, we need the lower fence and the upper fence. So lower fence is quartile 1, which we got up there was 91.5, minus 1.5 times the interquartile range, which is 23.5. Run that calculation, we get 56.25. And the upper fence, we start with Q3, which is 115, plus 1.5 times 23.5, which is 150.25. So if we go back and look at our data set, so bear these numbers in mind, 56.25, 150.25. Our lowest data point is 85. That's within that range. Our highest data point is 138. That's also within that range. So there are no data points that fall outside of these fences. So that tells us this one has no outliers. Which is good for us. We definitely like not having outliers. Now, when it comes to finding the 5-number summary, you'll see at the top of the next page here, they show you how to do it on the calculator. I'm going to show you how to do it on Desmos. It can be very quick and simple. Okay, so we're still using the weight data. So that's my W up there at the top. So let me pull this up here. Okay, so all we need to do, if you go into the functions on Desmos, notice there's a stats one right here. You can see a min button and a max button, but I'm not even going to use those. I'm just going to use the quartile button. You can also just type in quartile. Okay, and I'm going to do the quartile of W. And the nice thing about what Desmos does is if I try to close that off, it says, hey, wait a second, there's a problem. Quartile requires 2 arguments. So it needs the data set, and it needs you to tell it which quartile you're using. This is very helpful that Desmos can tell you. That way you know kind of how to set it up. So let's find the first quartile. We found in the example, the first quartile was 91.5. And there we have it, 91.5. Then to find the second quartile, that's just 110. And to find the third quartile, put in 3, and we get 115. Now the nice thing about the quartile function, we don't even need to use the max and min functions, because if you think about quartiles 1, 2, and 3, just picture the minimum as quartile 0, right? There's 0% of the data beneath it, and that's 85. Okay, that was our min. And think of the max as the 4th quartile, right? So it's up there, 100% of the data is below it, so we put 4 and 138. That is our maximum value. Okay, so just using the quartile function on Desmos can get us those values really quickly since we already have the data set plugged in here. All right. So next up, interpreting percentiles, quartiles, and median. So let's go back and look at this example. Looking at the cumulative relative frequency column, determine the 78th and 34th percentile. Where does the median lie? Okay, so remember when we're talking about relative frequency, we're talking about what portion of the whole is in that section. So for example, we're looking at number of cars in a household. 8% of houses have 0 cars, 26% have 1 car, 44% have 2 cars, etc., etc. When we're looking at the cumulative relative frequency, we're taking those values and adding them as we go. So this says 8% have 0 cars, 34% have either 0 or 1, right? Because it's 8 plus 26. 78% have 2, 1, or 0. 92% have 3, 2, 1, or 0, etc., etc. So now let's use the cumulative frequencies to find the 34th percentile, and the 78th percentile. And then we'll figure out where the median is. Okay, so the 34th percentile, that's going to be right there. 34% of the data lies beneath this value. Okay, 34% of the data lies beneath this value. So that means the 34th percentile is going to be 1 car. Then the 78th percentile, so 78% of the data lie beneath that value. So that means that the 78th percentile is 2 cars. Okay, so 78% of people have 2 cars or fewer. And then the median, so the median is where 50% of the data is above and 50% is below. Well, I know that 34% is below this, 78% is below that, and 50% is somewhere in between those two. Okay, so the median has to fall between these two values. Now, this 78 encompasses all of the 2's, the 1's, and the 0's. The 34 only covers the 1's and the 0's. So this tells me that the median is actually going to be 2 cars. Okay, and you just picture, like, if I actually listed these out, I'd list 4, then 13 more, then 22 more. The median is going to be somewhere among those 22. Okay, somewhere among those 22 households is where the median would be, right there in the middle. Right? So we can read these off of frequency tables as well. Okay, let's look at another example. So on a timed math test, the first quartile for the time it took to finish the exam was 35 minutes. Interpret the first quartile in the context of this situation. So we have Q1, the first quartile is 35 minutes. So what does this tell us? Well, this means that since it's the first quartile, 25% of the data is less than this. So 25% of students took less than 35 minutes to finish. That's what it's telling us. Okay, which means that 75% took more than 35 minutes. Okay. And then for the next example, taking the obtained information from 2.8, interpret the median. So example 2.8, that was the weight example. So go back up here. That was this one. Okay, so interpret the median. The median we got was 110. So that means that half the models weigh more than 110 pounds, and half weigh less than 110 pounds. Okay, that's what the median tells us. All right. So now, heading into section 2.4, we're still talking about quartiles, we're still talking about the median, talking about this interquartile range, but we're going to look at how we can visually represent these values, and that is using a box plot. So a box plot is a graphical representation of a 5-number summary. It's sometimes called a box and whisker plot. This is what a box plot looks like. The box plot highlights, using a box, where the first and third quartiles are. Okay, you draw a rectangle for those two. You draw a line, vertical line, to represent the second quartile, or the median. And then from the edges of the box, you draw lines. These are called the whiskers. That's why it's called a box and whisker plot, to the minimum and to the maximum. Okay, so that's how we draw a box plot. Okay, and we can also represent outliers on this, and we'll see an example of that soon. Okay, so let's look at this example. So every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the U.S. The following data are the interest rates charged by 10 credit card issuers randomly selected for the July 2005 survey. Determine the 5-number summary of the data from the calculator. So this one, we'll just go through it quickly. So we need the 5-number summary. So the minimum, first quartile, second quartile, third quartile, and the maximum. So the min is the smallest value, that's 6.5. The max is the largest value, which if you go through, that's going to be 14.5. Okay, the median is the middle value. So what you would need to do is you need to write these out in order, right? Because notice they're not all in order, right? Some of them are kind of out of place here. Once you list them all out in order, do exactly like we did in the previous example. Find the middle. In this case, there are 10 data points, so you're going to have to find an average. That'll give you 13.6. A good one to practice if you're wanting some extra practice with finding these quartiles. And then do the same thing we did on the last one. You get the first quartile is 12, third quartile is 14.4. Okay. Now to construct the box plot, you get the 5-number summary, you draw the horizontal axis, okay, to give you scale, find the fences, locate the quartiles, and draw the vertical lines, okay, draw the horizontal lines, finish your box. You can label the fences using brackets and place an asterisk for any outliers. Okay. One important note, it is important and required that you draw a horizontal axis with correlating tick marks, otherwise the box plot is not to scale. Like, it doesn't tell me any information unless I see that scale on the horizontal axis. Okay, so let's do that. So I'll draw my horizontal axis. All of the data points in here, go back and look, are between like 6 and 15. So let me go ahead and put a scale on here. So I'm going to start at 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Just go up to 20. Okay. So that gives us our very important scale. And now we start drawing our boxes. So we've already found the 5-number summary. So let's go ahead and put those in. So we've got the 6.5 for the min, the 14.5 for the max, and then we've got our Q1, Q2, Q3. So 12, 13.6, and 14.4. So we've got 12, 13.6 is right around here, and 14.4 is right in there. There we go. Let's go ahead and finish off that box. Okay. So again, here's our Q1, Q2, Q3. Now, before we draw our whiskers on this, I also want to look at the fences. So we need the IQR. That's going to be 14.4 minus 12, which is 2.4. So that's going to give us our lower fence and our upper fence. So lower fence is Q1, which is 12, minus 1.5 times the interquartile range. That is 8.4. And the upper fence is Q3 plus 1.5 times the interquartile range, so 2.4. And that is 18. Now, on the upper end of this, so 18 is where our upper fence is. So right there, that's our upper fence. Our maximum value, which was 15, falls within that. So I'm going to go ahead and draw a little tick mark for 15, and then connect that. But on the lower fence, notice the lower fence value is 8.4, but one of our data points, the 6.5, the min, is actually below that number. So that is actually an outlier. Okay, so what do we do when the min is an outlier? Well, we go ahead and just make it an outlier, so draw it as an asterisk, and then the box plot, so that whisker, will only go to whatever the next lowest number is. Okay, so let me draw the fence first. So our fence is at 8.4, so it's right about there. We're going to have our value of 6.5 is out here. It's an outlier, so that's going to be right here. So we draw a little asterisk. And then our new value that's going to be within the fence will be 9.9. Right? If you look, that's the next lowest number, 9.9. So right about 10 here, we're going to have just our little tick mark, and then connect it like that. Alright, and that is our box plot. Okay, so we can draw a box plot. Notice when you're doing the 5-number summary, 6.5 is still the min. Okay, so numerically that's still the minimum value, but when drawing the box plot, it is considered an outlier, so we just stop the box plot at the next lowest value that's inside the fence. Now, when you're doing these using like technology, so on Desmos, let me show you. So there is a box plot function on Desmos. If I can, oh, there it is. So you see box plot right here, right across from histogram. So you can draw a box plot of anything. So let me just do one with my set W. Okay, and there's a box plot. Desmos will draw it for you. The one thing that Desmos does not do, it does not identify outliers for you. So if you just look at the box plot on Desmos, that's not going to tell you if there are outliers. So you still have to make that determination for yourself, and that'll help you in completing these drawings of the box plots.